All right, hi everyone. Today we are going to kind of shift gears to proofs. So the last few weeks we've been dealing with logic and the symbols that we can use to kind of shorten our proofs. So really the last couple of weeks have been a foundation for what we're going to start today. So this is sort of just a continuation of the unit, so this is just going to be 7.06, and then this is the direct proofs and disproofs. So let's start with just a few definitions. So first we're going to say, suppose A is an integer. And just to refresh ourselves on what an integer is, that is essentially just a whole number that is, it could be positive or negative, and it doesn't include any decimals or anything like that. So there's one symbol that I want to start with, and we'll dive deeper into this later at some point, but we can define the whole set of integers. So every single integer that there is in the whole world, from positive infinity to negative infinity, can be represented using this sort of Z shape. So if I want to say that A is an integer, I can also rewrite this using symbols as A is an element of, so this sort of curvy E looking thing here means an element of or belongs to the set of, and then we can say integers. So you can either create it like this, which I don't prefer doing it this way. I just kind of write a Z and then put a slash in it, and then a double backbone to this Z. But either way that you prefer to create it, that is known as the set of integers. So from now on, instead of writing out the word integer, I'm just going to say whatever this sort of phrase here, element of the set of integers. So from now on, if you see this Z with a double backbone, that indicates that you are talking about an integer. So for our first definition here, A is even means, so we're talking about the definition of even and odd. If we were in class, I would rather have you all sort of define this, and then I would define it, but we're working with what we got. So if A is even means there exists, so that quantifier that we've been talking about, there exists a j that is an integer such that a equals 2j. So if a is an even number, basically what this means is it's divisible by 2. And we can define that as long as j is an integer. If we are divisible, that means we have no remainder, so j would have to be an integer. On the other side, however, if a is odd, this means, again, that there exists some, let's just put k, since we're not double dipping with j here. There exists a k that's an integer, so there exists, again, that quantifier, such that a equals 2k plus 1. So if a is an odd number, then that means that technically we could subtract 1 from a if we were to solve for k, and then once we subtract 1 from a, then a would be divisible by 2. So essentially, since we alternate between even, odd throughout our integer system, if we were to subtract by 1 and it's an odd number, then automatically it would bump us down to an even number. So that's where these definitions come into play. So following these definitions, we have a postulate or an axiom. So this is something that isn't necessarily proven. An axiom is something that is just accepted in the math community that doesn't need a proof. So this is called the parity axiom, or parity postulate, whichever you prefer. So the parity axiom says that every integer a is either even or odd but not both. So you could probably write this as a quantifier. So we could say, let's actually just write this out. This isn't in my notes, but I would like to share this out. So if we let a be the statement any integer, so a is any integer, e is a is even, o is a is odd, then we could have the statement for all a, e exclusive or o. So this statement right here is this statement here. So for all a, either a is even or a is odd, but not both. So now that we have this definition here, we have this axiom, we can go ahead and prove some statements. So let's go ahead and do our first example. So looking here, we kind of start with the same thing. So suppose a is an integer, so a is an element of the integers. We want to prove that if a is odd, then 3a plus 5 is even. So we have an if-then statement here. So the way that we prove an if-then statement is we kind of start with, or we assume the if part. So it's saying if a is odd. Okay, so let's assume a is odd. So then we prove the then half of the statement. So let's just go ahead and assume a is odd. So we kind of write this out with proof, and then we assume the if part. So assume a is odd. And then after we've made an assumption, we want to hit this assumption with a definition. So we just defined what odd means. So we can say by definition of odd, and I just always really abbreviate definition with def here. So by definition of odd, there exists a j that is an integer, and a equals 2j plus 1. I know in our definition we used k, but since we haven't used k or j yet, we can just go ahead and stick with j. So again, to recap, we assume the if part, and then we hit that if part with the definition of whatever we assumed. And so now we know what a is equal to. We said by definition a is equal to this. So I'm trying to prove a statement about a. I'm trying to prove this statement. So now I can go ahead and just substitute in my a value into this expression and work it into being even. So you'll see what I mean in just a second. So consider the following. So here we can start with our then part. So we have 3a plus 5. And again, I just defined a, so I can go ahead and make a direct substitution into this formula here. So 2j plus 1 and then plus 5. So over on the right-hand side, I'm just going to justify each of my steps. So here I just subbed in a equals 2j plus 1. And now, excuse me, we're going to just distribute this 3. So we have 6j plus 3 plus 5. So this is our distributive law. And then we can go ahead and simplify. So 6j plus 8. So I can write simplify or combine like terms, whichever you prefer. And then this is going to be equal to, and I'm going to factor out a 2 here. And you'll see why I'm going to do that in just a second. But essentially, again, I'm trying to prove that this statement here is even. So I need to make this mimic the definition of even. So if I factor out a 2, I'm left with the quantity 3j plus 4. And now I'm going to, again, do something that's probably not intuitive, but once we continue with these proof methods, you'll get used to the idea of doing this. So we're subbing in another variable, and we're letting that variable be equal to the quantity that we're left with after we've factored. So now I've worked the statement 3a plus 5 into the statement 2m. And now this looks like the definition of even. However, there's one piece that we need to include. So if I go back to my definition of even, it says a is even means there exists a j that's an integer such that a equals 2j. Well, we have this 2 times something part, but we need to show that we are in the set of integers. So essentially we need to say if m is equal to 3j plus 4, how can I guarantee that that is an integer? Well, we said before that an integer is a whole number. There's no decimals, no fractions, or anything like that. So since j was an integer and 3j plus 4 has no fractions or decimals, then there exists an m that is an integer such that 3a plus 5 is equal to 2m. So again, we need this statement here essentially to say that m is an integer. So since j was an integer and m is made up of 3j plus 4, and the statement, the expression 3j plus 4 has no fractions or decimals, we can assume that there exists an m that is an integer, and then our statement here can follow. So because we have this final statement here, by the definition of even, so from our definition here, 3a plus 5 is even. And we just proved what we are trying to prove above. This little sort of habit that mathematicians are involved with after we finish a proof, when it's our final statement, we've just proved what we wanted to prove, we just put a little shaded box at the end of our proof. to indicate that we are done. That is our final statement. There is nothing else to show. Some mathematicians also, instead of the filled in box, might just write QED. That is a acronym for something that is blanking me at the moment, but a lot of, I don't want to say older mathematicians, but mathematicians who've been around for a while, at least in my undergrad, most mathematicians who were well into their 60s, they preferred the QED. Mathematicians who were sort of younger, fresh out of grad school, they like to use the filled-in square. So whichever you prefer, they both mean the same thing, that our proof is done. Okay, so let's go ahead and do a little bit more of a complicated proof, but still following the same guidelines here. So our second example, we have, again, suppose A and B are integers. Prove that if both A is even and B is odd, then AB minus B is odd. So again, our proof method here, if we have an if-then statement, we assume the if part and we try to prove the then part. So we just start with proof. So assume A is even and B is odd. So we just assume something, so now we can hit it with a definition. So by definition of even, there exists, and since now this is a new proof, I can continue using J, so there exists a J in the set of integers. And then I'm going to abbreviate such that with ST. So again, mathematicians were lazy. We like to abbreviate as much as possible. I'm sure some of you can identify with that. So from now on, we'll just abbreviate such that with ST. So there exists a J that is an integer such that A equals 2J. Now by the definition of odd, there exists a K that's an integer such that B equals 2K plus 1. So we've exhausted our definitions here, so now we can jump into the proof part. So consider the following. So start with our then part. So we have AB minus B. And now we know what A is equal to, we know what B is equal to, so we can go ahead and sub that in. So we have 2J, 2K plus 1, minus 2K plus 1. So we just go ahead and sub in A equals 2J, B equals 2K plus 1. And now we can simplify, so we need to distribute here, so we are left with 4JK plus 2J, and now we have minus 2K minus 1. So we're just distributing here. And now, again, this step might not be counterintuitive, but we need to think of what our end goal is in mind. So our end goal is to show that AB minus B is odd, and we need to match the definition of odd in some way. So we need to be left with 2m plus 1. So I need that plus 1 to come from somewhere, and I need to be able to factor out a 2. So looking at this statement here, I have a minus 1. Well, that doesn't match my definition of odd, so I need to make this into something that is plus 1. So I'm going to manipulate this negative 1 here to include a plus 1. So in order to do that, I'm going to have 4JK plus 2j minus 2k. So nothing happens with our variables. But this last step here, again, this is not counterintuitive. This is just a trick that I need to show you, and now you'll know it, and then you can use it later on. So I need a plus 1, so I'm going to essentially sub in minus 2 plus 1. And if I simplify that, I get back to negative 1. So that's totally legal. It's fine. So we can just say that our justification is rewrite negative 1 equals negative 2 plus 1. Sorry, this is really squished here. So negative 2 plus 1. So now we have that plus 1 that we need, and if you notice, every other term in this expression is now divisible by 2. We can factor out a 2, which is exactly what we want to do next. So now we factor out a 2, and we're left with 2jk plus j minus k minus 1. And then I don't want to factor out a 2 from this last term because I want to be left with a plus 1. So just factor a 2. And now we can see, okay, so just like that trick we did before, we are left with 2m plus 1. And we can just sub m equals 2jk plus j minus k minus 1. And so now, essentially the same thing that we said before, m has neither fractions nor decimals, so there exists m that's an integer. So let's just write our final statement here. So since m has neither fractions nor decimals, there exists an m that's an integer such that ab minus b equals 2m plus 1. So by the definition of odd, ab minus b is odd. We're done. That's our proof. So, oh, excuse me. I don't want to put m here. I want to put what m is equal to. So since let's kind of caret this in, since 2jk plus j minus k minus 1. That should be what's in here. So since 2jk plus j minus k minus 1 has neither fractions nor decimals, there exists a m such that ab minus b equals 2m plus 1. So again, these direct proofs, they kind of follow the same methodology. We assume the if part, we hit them with our definitions, and then we work the then part into the statement that we want to show. So again, if we're trying to prove that something is odd, we want our final statement to be 2 times a variable plus 1, because that meets our definition of odd. So sometimes when we get further into more complicated proof methods, more complicated statements to prove, sometimes it might be beneficial to start with what you want to end with and work your way backwards. So starting perhaps if you know that you want to end up here, and you just need to figure out how to get there. So if this here, rewriting negative 1 as negative 2 plus 1, that might not be intuitive. But if we were to start with what we wanted, we might be able to work ourselves there. So don't panic if this is something that you wouldn't have thought of right away. It's definitely something that I didn't think of right away. But as you get closer, as you do this more often, the closer and closer you get to, thinking in this methodology. Okay, so the last 2 examples were just direct proofs. So now we're just going to do a disproof here. So essentially, the way that we do a disproof is to think of a counterexample. If you can think of a counterexample to a statement, then you have disproved your claim. So if we start with the statement, again, suppose a is an integer. If a is odd, then a squared plus a plus 1 is even. So instead of writing proof here, I'm going to write disproof. And let's just pick an integer for a. So suppose, or let's consider a equals 3. So we know a is 3, so observe that a is odd. And if I sub in 3 into my statement, then a squared plus a plus 1, if I sub in 3, I would get 13. And that is not even. So thus, a equals 3 is a counterexample. And the statement is disproven. So again, note, it only takes one counterexample to disprove a claim. So it only takes one counterexample to disprove a claim. So when we were doing the proofs, like in the last two examples like this, we are proving this in full generality. We are proving this for all sets of integers, and we do that so that we can say it doesn't matter what a is equal to, as long as it meets the definition of even or it meets the definition of odd. We can prove it for every single integer that is even or odd. If we want to disprove something, then we are saying that, well, it's not true for every single integer, so you can't make this generalization. And so it only takes one to disprove it. So as you can see, it's really difficult to prove things, because if it only takes one statement to disprove it, how can you be 100% sure that every single integer from negative infinity to infinity will meet that criteria? And that is a difficult thing. Mathematicians have spent a long time of their lives trying to do that. And it is something that a lot of mathematicians have mastered, and there are proofs out there that have not been proven because it is so difficult to prove it in full generality. So this is something that we're going to continue to work at, and we're going to do different proof methods as we continue this. So with this, we're done for today. If you have any questions, please feel free to email me. Other than that, I will hold the Zoom call for this tomorrow with the classwork. So you do not have any formal classwork. There's just a Google form just to meet the attendance requirements to say that you've watched this whole video in its entirety. So again, if you have any questions, please feel free to email me. Other than that, we can chat tomorrow. All right, have a great rest of your day, everyone.